So normal probability distributions. This is a very important topic that we'll be discussing today. So if you learn like one topic, it's definitely, this is like the most, I don't know if I should say the most important, but it's a very important topic used in statistics and probability. So we're going to identify the characteristics of a normal distribution. We're going to calculate these things called Z values. And this is of utmost importance again and again and again. You'll definitely see this on your test. You'll definitely see this on your final test. Calculate the area under the standard normal distribution using Z tables. Identify properties for a normally distributed variable by transforming it into a standard normal variable. Calculate specific data values for given percentages and using the standard normal distribution. And then explain central limit theorem and use it to solve problems involving sample means for large samples. So we're going to be essentially talking about normal probability distributions. So a normal distribution looks like this. Next week is Halloween, so that's kind of cute. No classes next week, by the way. So when describing, because we have reading week, so when describing frequency distributions, we define a few regularly occurring shapes in statistics. Mound shape, so we know what mound shape is, uniform shape, skewed right or skewed left, etc. So several times you may have heard me refer to this mound shape, again, as a normal distribution. This is because there are not only the same, but they tend to be one of the most common, so very most common types of distributions. Think of it as the Swiss Army knife of statistics. So the graph of a normal distribution is called basically a normal curve. And it possesses a shape very much like the cross-section of a pile of dry sand. Because of its shape, blacksmiths would sometimes use a pile of dry sand in the construction of a mold for a bell. Again, another word for this is bell curve. So thus the normal curve is also called a bell-shaped curve. So there's lots of words. So normal, bell curve, etc. So continuous random variables can assume infinitely many values corresponding to points on a line interval. And this is very important and used in statistics like height, weight. There are continuous random variables, length of a life of a particular product like time, experimental lab error, test marks. Students typically, this is very important for students. It used to be very important for me when I was a student, like if this is the average, this is the mean, and some students are up here, they're getting like, let's say 90%. Some students are down here. Like, where am I on this bell curve is what I would think if I were a student. So as the number of measurements become very large and the class width becomes very narrow, the relative frequency histogram appears like a smooth curve. So before, we had this discrete case of X times the relative frequency, and it was a histogram. And then when we make these very, very small, we can see it starts to look like something that we're very familiar with, which is this normal curve or bell curve. So what is the normal curve? Well, here at the top, we see that this is the mean, which another fancy word is average. Here we have the mean plus the one standard deviation. Here is the mean plus 2 standard deviations. Here it's plus 3. Here's the mean minus one standard deviation. Here's the mean -2, and here's the mean -3. So what does this mean? So at one standard deviation, you see that there's actually inflection points here. The concavity sort of changes slightly here and here. And so remember like this picture of, because you see it again and again in this particular shape. Let's put a little star to remember it. Now, some key features of the normal curve are, you can see that it's symmetric. So it's very symmetrical around the mean. The highest point is, of course, where the mean is. Like this is the highest point, which is another word for average. Inflection points happen at one standard deviation above or below the mean. So right here and here. The area under the curve is equal to 1 or 100%. So all this area under the whole curve is equal to either 1 or in a percentage 100%. Almost all of the data is within 3 standard deviations of the mean. You see over here and over here, from here to here, all this area in here. You can see that it basically composes of the majority of the data, and it's asymptotic to the horizontal axis. You see, as the axis extends, let's extend it. Sorry, this gets closer and closer and closer and closer and closer and closer. I can't draw so well with this. But it gets very close to the x-axis, but it doesn't actually cross the x-axis. So what is an acetope? So one thing to remember about what asymptotic means is that it continuously approaches, let's say, I'm walking towards this person, but I never reach the person. Suppose this person's also walking that way at the same kind of rate, at the same speed or something like that. So, and same acceleration and all that. So I never actually reach the person. So it's a bizarre concept for sure, but it turns out very frequently in mathematics. So you never actually reach the person. So a normal distribution has an asymptote along this horizontal axis, and this takes into account that distributions could have extreme outliers, points far away from the mean, and recognizes that they are increasingly less likely, but in general, never completely impossible. So there's possibilities that you'll get a point all the way out here. Like it's very unlikely, but that's possible. So consider this normal curve. We have like this normal curve. Do the distributions have normal curves? The curves. So do like these distributions have the same mean? If so, what are they? Well, you see that the mean was here and here. So the mean is 6. So for A and B, they have the same mean. Yes. So yes. And if so, what are the means? The means are both 6 for A and for B. So one of the curves corresponds to a normal distribution with our sigma, our standard deviation is 3, and the other one is their standard deviation is 1. Which one? Well, standard deviation, remember the sigma means the spread. So how far away is it spread out? So a larger spread is going to be this kind of shape. It's more spread out. So that would be B. So B would be sigma over 3. A smaller spread would have like this shape, which would be A. So in the past, you may recall that to produce a graphical representation of a line, we use this general equation. We all know y equals mx plus b, and you use this very frequently in AI. Like this is can be used in AI, like a more advanced format, of course. So the equation that gives us the graph of a normal curve is actually this guy. Ugh. But this is kind of complex. It has an exponential function to the exponent negative 1 over 2 x minus mu divided by our standard deviation. This can square divided by standard deviation times the square root of 2 pi. Yikes, right? So this 2 pi can be difficult to deal with unless you know some calculus. So the mean is equal to the population mean, and the standard deviation is equal to the population standard deviation. So based on this complexity alone, it's safe to assume that we will not be using this equation explicitly because you'll probably need to know some calculus in order to deal with it correctly. But there are a few things to note about it. Clearly, it depends on the mean and the standard deviation. You can see this. So that's the main thing. So the continuous random variable types. There are many different types of continuous random variable. So we want to try to pick a model that fits the data well, of course, and allows us to make the best possible inferences, keyword here, using the data. So the area under the curve. So the area under the curve is equal to 1. We know this. So actually the probability is equal to the area for the random variable between, let's say, a lower bound and an upper bound, A and B. It's actually equal to the area under the curve between A and B. So let's say we have this f of x, and f of x is this guy. And we have x. So, and we have our normal distribution here. So this is the probability under basically the curve. So since the area under the curve is equal to 1, it can be used to represent probabilities. The proportion of the area under the curve about a given interval represents the probability that a measurement will lie in that interval. So we recall Chebyshev's theorem gave us information about the smallest proportion of data that lies within 2, 3, or k standard deviations of the mean. So this theorem could be applied to any distribution, but we find that with normal distributions, we get a much more precise result, which is given by this empirical rule. So instead of Chebyshev's, we can even find something a little bit better than Chebyshev's theorem, and it's called this empirical rule. So what is the empirical rule? So it is for a distribution that is symmetrical. So it has to be symmetrical, and it has to be bell-shaped or normal. So normal shape distribution. Approximately 68% of the data values will lie within 1 standard deviation on each side of the mean. Approximately 95% of the data values will lie within 2 standard deviations of each side of the mean, and almost 99.7%, so almost all, of the data lie within 3 standard deviations on each side of the mean. So it's called the empirical rule because for symmetrical, bell-shaped distributions, the given percentages are observed in practice. So we notice that the empirical rule is a stronger statement than actually Chebyshev's theorem, in that it gives us definite percentages, not just like lower limits. Of course, the empirical rule applies only to normal or symmetrical bell-shaped distributions, versus Chebyshev's theorem applies to all distributions. So there's a difference. Now, so the depth or density of the probability, which varies with x, may be described by this mathematical formula f of x, and that's called the probability distribution or probability density function. So for the random variable x. So the standard normal distribution, so is n is equal to where the mean is 0 and the standard deviation is 1 by definition. And this is called the standard normal distribution, and we put this n to denote the normal part. So if you shift the mean left or right, you're going to shift the bell curve left or right. If you change the standard deviation, you stretch or constrict the curve. If, for example, like sometimes when I went to university, I went to U of T, and in the first, I took a very difficult course, and they are like, oh, we're just going to bell curve everyone, etc., things like that. So that means they're going to shift this curve. But it also means that it just means the curve part shifts. So the average shifts, but if you're down here or up here, you don't shift this much. So these people might move a bit, the most, these people move less. So this is what the shifting could mean. So the area under a normal curve. So remember, we have like this mean here, and 68% lie within one standard deviation. So from here to here would be 68. So all of this is 68. Which is 34% and 34%. I think the next one was, oops. Just calculating. 95, so from like here to here, all this is 95, etc. And you can see, so this would mean there would be 34% in this area and 34 in this area. And you could do the math. You could say 95 subtract 64 divided by 2 is 13.5 and 13.5. And then we have like these little areas as well. Oh, here it is down here. Sorry. And this is 95. And then we have 99.7. So those are the probabilities, essentially. So the plane life of a sunshine radio is normally distributed with this particular mean of 600 hours. So that is our mean. And our standard deviation is 100 hours. What is the probability that a radio selected at random will last between 60 to 100 hours? So what is this probability between here and here? So we could plot it. We could say, okay, and so if we actually plotted it on this particular picture, we can see that this is 600, this is 700. 600 plus the one standard deviation is 100. So plus 100. So we have our mean plus our standard deviation. That would be 600 plus 100 is obviously 700. So this area So the probability between 600 is less than or equal to x less than or equal to 700 is going to just be 34% because it's just that area underneath the curve. The yearly wheat yield per acre on a particular farm is normally distributed. So we know it's normally distributed with a particular mean of 35 bushels. So that is of course, our mean here of 35. And a standard deviation of 8. Shade the area under the curve that best represents the probability that an acre will yield between 19 and 35 bushels. So we could calculate this. So we could calculate essentially 35 subtract 8 is, because that's so 35 minus 8 is 27, which is here. So this is our mean minus our standard deviation. And then the next one, subtract 2 times 8 is 19. Whoops, 19. Which is here. So this would be all the area, all this blue here, representing the probability. So this would represent the probability between 19 is less than x is less than 35. Would be all this like blue area. So is the area the same as the area between the mean minus 2 and the mean? Well, yes, obviously, we just kind of did that, yes. Use the area from the empirical rule to find the percentage of the area over the interval between 19 and 35. Well, we know like half of this, and we could use a different color to maybe see this a little bit more. We know that this is going to be essentially 34. And this was, I think, 13.5% here. So we could add them up and we could get 47.5%. So what is the probability that the yield will be between 19 and 35 bushels per area? So that is the probability between 19 and 35. So that's, again, going to be 47.5%. In summary, what does a normal distribution tell us? If a continuous random variable has a normal distribution, then the area under the entire curve is 1, which we know the area over a specified interval of values from A to B is the probability that a randomly selected value falls between A and B. The distribution is, of course, symmetrical in mound shape and is centered over mu. And most of the data, 99.7%, range from basically 3 standard deviations above or below the mean. The standard normal distribution curve, section 7.2. So normal distributions vary from one another in 2 ways. The mean may be located anywhere on the x-axis. The bell shape may be more or less spread according to the size of the standard deviation. So we can look at these things called z-scores. So z-scores. So by definition, a z-score is the number of standard deviations. So how many steps above or below the mean? So for example, this is a normal distribution would work for a z-score. So it's the x-axis is now a z, and we have our mean here. And this would be 1 standard deviation, 2 standard deviation, or this is 1, 2, 3. This is -1, -2, -3, and it corresponding to the number of standard deviations. So this is our plot of our Z-scores. And again, it's kind of the same except for the X. Before we had X, before we had the X-axis. Now we have the Z. So now it's a Z axis, essentially, and the rest of the information is the same. So we will refer to the original data as the raw data, while the new points on the standard normal distribution that they have been mapped to are referred to as the Z-scores. So it's basically a mapping from the X, the raw data, and it's mapped to a Z-score. So we do something and we get this. Since the Z-scores are created with a standard deviation of 1, their values will always be the number of standard deviations between the original measurement and the mean. So this is what we do. So converting between raw data and Z-scores. The Z-score and raw data point of a sample can be converted between each other. So we're doing that conversion. So essentially we have our raw data, X, we subtract the mean, and we divide by the standard deviation. That is our Z-score. So that is how we go from raw data and we apply this and we get our Z-score by doing, like, again, I'll write that out again, by applying this transformation to our data point. We have our data point and then we have this data point. Now, when we have like this data point, which is our Z-score, we can get back to our raw data here by applying another transformation, which is this. Just X is going to be equal to Z times our standard deviation plus our mu. So this goes this way, and this one goes this way. Like if for Z to X, from X to Z, this is from Z to X. So if we have this and we have these, we can get our X. If we have this and this and this, we can get our Z. So this is so the mean is a very special value of the distribution. So we can see what happens when our X is basically 0. So when X is equal to 0, you see that we have 0. And if our mean is equal to 0, what happens? Sorry, whoops. Not 0. So when our X value equals to our mean, we have a special case. Let me re-say it. Sorry, I'm skipping ahead. So when our Z is going to be equal to our X minus our mean divided by our standard deviation, we're going to have, if our X equals our mean, that point at the top is going to be, why do I keep writing 0? That point is going to be our mean minus our mean divided by our standard deviation, which is equal to 0. I keep skipping to the step. So we see that that point at the top they're exactly the same curves, but so if this is our X and this is our mean here, for our Z table or score, this is going to be 0, and this point gets mapped to our 0. So this makes the mean of the original distribution is always 0 in standard units. So this makes sense because the mean is 0 standard variations from itself. An X value in the original distribution that is above the mean has the corresponding Z value that is positive. So you can just draw like a little picture to kind of understand this. So if this is X and this is our mean, then again, this one would be 0. And if X were greater than the mean on this side, then Z would be greater than 0 on this side. If X were less than mean on this side, then there would be negative on this side. On this side is X is greater than the mean. This side is X is less than the mean. So you can kind of see why. That's what I'm saying all in here. So let's compute the Z scores of the following. So a raw score, there's of 165 from a population with a mean of 150 and a standard deviation of 15 is this information. So we want to compute this, so find like these Z scores. So we just take Z. So the first thing is to notice the mean is 150. So that would be the top point. And we want to find this raw score. So this is our X. Let me clean that up a little bit. So this is our X. And it's essentially what we're trying to find. And we have our mean and we have our standard deviation. So we can draw like this like little bell curve out, and we see X minus mu divide our standard deviation. We plug in the numbers and we get 1. So this corresponds to essentially a transformation from the raw data to a Z score by like this way. And this corresponds to the mean is at 0. So this is the Z axis versus this is the X axis. And this 165 gets transformed into a 1 because of this at this particular point. And you can then draw the rest on it nicely and symmetrical. And you would see that this is the standard, and it has a standard deviation of 15. So that means it's 1 standard deviation away. So there should be an inflection point here. For the next one, a raw score of 105 from a population with a mean of 125 and a standard deviation of 10. So we have the mean here is 125, and it's going to be mapped to 0. So, and we have a raw score of 105. So we could say just because these are whole numbers doesn't, you can have decimals, and we'll see some examples. So, so this is the mean, and it's obviously going to be mapped to the 0 at 105. So we could kind of like draw a picture, and we could calculate it, and we can see the Z score is going to be -2. So it's going to be 1, 2, -2. So it's actually the Z score in this particular case, it's 2 standard deviations away from the mean. So if we were to draw this again, it's not at the inflection point here, it's going to be down here. And we could draw it this particular way, and then we could see like we're trying to find like this raw score, and we could also map this, and they would have exactly the same shapes. Now let's compute the raw score. So now this time the raw score from the following. So we have a Z-score, let's say of 0.55 from a population with a mean of 95 and a standard deviation of 5. So now we want to work backwards in a sense. So we're in this situation, we have the mean of 0. We can draw 1, 2, 3, and we have a Z-score of 0.5. So we can draw this right here. And we want to find the raw score here. So it's just going to be x equals z times that standard deviation plus the mean. And we got 97.5, which is about here. And the question gives us a mean of 95. And then we could see, okay, about 1 would be about we could also calculate this one if we wish, which is about 100. Now, the next one, if we have a Z-score of 1.5, let's say this is our negative 1.5, from a population with a mean of 80, so this is 80, and a standard deviation of 10, we can calculate this to be 65. And then we can draw this, okay, so negative 1.5, it's not 1, it's not 2, it's in here. 80 is again the mean. So this corresponds to 65 about here. And then we can draw it because the standard deviation is 10. So we could like label our axis, etc. So a pizza parlor franchise specifies that the average mean amount of cheese on a large pizza should be about 8 ounces. And the standard deviation only about 0.5 ounces. An inspector picks out a large pizza at random in one of the pizza parlors and finds that it is made with 69 ounces of cheese. Okay, so assume that the amount of cheese on a pizza follows a normal distribution. If the amount of cheese is below the mean by more than 3 standard deviations, this parlor will be in danger of losing their franchise. So essentially find the Z-score. How many standard deviations is the keyword here to find that Z-score from the mean, which is 6.9 away from the mean. Is the pizza parlor in danger of losing its franchise? So we have essentially the mean was here. So this is the average. So when you see average, you know the mean is 8. The standard deviation is here, and this is our raw data, x. So we can write it out and we can calculate our Z-score. So again, this is our mean, it's about here. We have our standard deviation is 0.5, so we can put it on our x-axis. 7.5 this way, 8.5, 9, 9.5, 7, 6.5, because we have this. And we can, we see that it's negative 2.2. So we could label negative 1, negative 2, negative 3. We found our Z is about here. And then we can see that if we draw it, it's about here. In terms of our raw data is 6.9. So it's about here and here. So therefore 6.9 ounces is it's only 2.2 standard deviations below the mean. So below that average. So this was the average, and this is how much in this particular sample we get. So the franchise is safe because they would lose their license if it's below 3 standard deviations, but they're okay. So Rod figures that it takes an average mean of 17 minutes with a standard deviation. So 17 minutes with a standard deviation of 3 minutes to drive from home, park the car, and walk to an early morning class. So it takes about this. One day it took Rod 21 minutes to get to class. How many standard deviations from the average is that? Is the Z-score positive or negative? And explain why it should either be positive or negative. The second question part B here is when commuting time corresponds to a standard score of Z equals negative 2.5, could Rod count on making it to class in this amount of time or less? So we have our mean, we have our standard deviation, and we have our raw data, X. So we could first compute A. Here, this is our A, as Z is equal to X minus mu divided our standard deviation. We have 21 minus 17 divided by 3 and get 1.33. We could draw this on the graph as like this is our essentially our 17. That's our mean, and this is our Z, so it corresponds. And we have, we want to see where 21 corresponds to basically 1.33. So this is our 1.33, which we just calculated it. And we see that it is about 3. We can, our standard deviation is 3. So 17 plus 3 is 20 plus 3 is 23, etc. And so we see that our Z-score is basically positive since the raw data we are considering here is above the mean, because the mean is 17 and our raw data is 21. The second question corresponds to a standard score of negative 2.5. So if the Z-score is negative 2.5 down here, then our raw data would be, converting to our raw data would be negative 2.5 times 3 plus 17, get 9.5. So this would correspond to over here of basically 9.5. So therefore, no, he should not account for making it to class in less than 9.5 minutes, because such a small percentage of times area under the curve is below 9.5. So he probably, no. So an average of all of this is that if 2 or more, or so an advantage of all of this is that if 2 or more sets of raw data are converted to their Z-scores, they become extremely easy to compare. So consider like this example of 2 measurements. We have measurement 1 and 2, raw data, means, and so different means, different standard deviations, different raw data. So we can basically, which measure is relatively higher? So we can, it's a way to kind of normalize the data, right? This is the key word, is normalizing the data. So we can take essentially our Z-score of measurement 1 and measurement 2, and we see that this is much larger than this. So measure 1 is relatively higher in terms of versus measurement 2. Here, if we have this set of mean, standard deviations, and raw data, which measure is relatively higher? So we see that if we calculate the Z-score here versus this one, measure 2 is higher than measure 1. Because remember, it's on this, this is our 0. This would maybe be wherever, this will be negative 0.67, and this one would be over, let's say, 1.33 negative. So we're going to continue on talking about areas under the curve, section 7.3. This is an important topic. So areas under the standard normal distribution. So we have seen how to convert any normal distribution to the standard normal distribution. We can change any X value to a Z value and back again. There are extensive tables that show the area under the normal curve for almost any interval along the x-axis. And there's this PDF file called Z-scores or normal table, which I'll show you in a second. So the areas are important because each area is equal to the probability. So this thing called probability that the measurement of an item selected at random falls in this interval. So there are, we're going to use the left tail style of this table for this particular Z normal distribution. Other distributions might use a right tail or a central tail or central, but this normal distribution uses this left tail. And this style table always gives the cumulative area, so the total area, cumulative area to the left of a specified Z. This may not be the area we are after in every question, so it's important to know how to draw more information. So utilizing this fact that the area under the curve, the whole curve is 1, we take advantage of essentially symmetry of the normal distribution. So for example, remember that it looks like this, where in the center, our Z is equal to 0. So these are our positive values. These are our negative values. So there's negative Zs on this side. This is our Z. Imagine there's a line here. I'm not going to draw that line because my handwriting's a little wobbly. But so there's negative values on this side and positive values, and it's symmetrical. So we take advantage of the symmetry to help us find these Z values. So let's look at what it is essentially. So we have like this Z table, and this is also uploaded into the content section. So when Z is equal to 0, that means 0.5, we can read this table this particular way. So this is the first and second digit, so this would be like 0.0, and this would be the next digit. We add these essentially to these values. So the first number is like, let's say negative 2.8 plus 0.02 would be this probability under this Z curve to the left. So 0.0, when Z is 0, essentially, the probability is 0.5 because half of it is on this side and then half of it would be on the other side. So 0.5 plus 0.5 is 1. Let's take negative 2.05 would be this value, and it would be on this side. Now there's positive values too. Again, when Z is 0, this is the probability is 5 on one side. And it can go all the way, this table, to 3.49. So the probability there, and these are the positives, and these are the negatives. So you just scroll. This one would be 0.9998. So it's almost over here. And the probability is almost all of it, except for a tiny bit of, so you can kind of like read the tables this way. So again, a Z table gives the cumulative, so it gives this cumulative area to the left, Again, it's to the left of a specified z-score. So if we have that z-score, then we can find the probability that a value is below the z value. So we find the associated z-score from the raw data. So we go from the raw data to the z-score. And from the z-score, we go to the probability. And we know how to also go back. And then also from the probability, you can go to the z-score. So keep like this idea of in mind. So you can go from here to here, and then here to here, and then from probability to z-score and z-score to raw data. So remember that the z-score for the raw data value is rounded basically to 2 decimal places. Locate the first 2 digits of the z-score, so the 1s and the 10s, in the leftmost column of the table, and then locate the hundredths digit of the z-score in the first row of the table across the top. And then you look at where the column and the row basically intersect to find that associated probability. So let's draw a diagram and try to understand the following questions. So the first one asks the area under the standard normal curve to the left of z equals -1. So here's the probability of z is less than or equal to -1.00. And so we can draw this, and this is our z, of course, and we have our 0, and we have -1 here. So we want to find like this area, this green area, where it is. So we can see at -1, so it's negative, so it's in the first part, -1.0, and then 0 is 0.1587. So this is negative, so 0.1587, and then we multiply it by 100 and we get 15.87%. The next one is the area to the left of z equals 1.18. So this would be on this side, it's positive, it's not negative, of 0. So 1.18, here's 1.1, and then we try to find the 8 down here. So I got 0.8810. Whoops. 0.8810. And then we can multiply it by 100 if we want that percentage. Sometimes we like to just leave it between 0 and 1. The next one is the area to the left of x equals 23.2 with this mean and standard deviation. Well, we want to convert it. So we know the mean is 26, and that converts to a 0. We have that our x value is 23, but we want to calculate that z-score. So we calculate 23.2 minus 26 divided by 3.2 and get -0.88. So this is the same as the probability of x being less than 23.2. Well, this x can be converted to our z. This 23.2 is converted to -0.8, because let me just try to draw it, re-explain. So x is less than or equal to 23.2. So this is the equivalent of saying x is equal to, well, if we take x minus our mean divided by our standard deviation, we know from inequalities from high school mathematics, it's going to be 23.2 minus that mean of 26 divided by 3.2. Whatever we do to the left-hand side, we do to the right-hand side. This is all equal to our z, and this is equal to, we just calculated, -0.88, which is how we make this, like essentially this transformation. Now we have negative 0.88. We can look that up in our table. Negative 0. So here's negative 0. And then 8. Okay, here's column 8. Right here, 0.1894. 0.1894. So we get our probability. So this is our probability, essentially. So, and then we can mark it on our graph. So we can put -1, 2, etc., 1, 2, 3. We have negative 0.88, and it corresponds to this value here of 23.2. And then we can shade the areas respectively. So also good to note the following. So treat any area to the left of a Z value smaller than negative 3.49 as basically 0, and any area greater of 3.49 as basically 1. So anything down here is pretty much 0%. And anything, if you have your Z is over here, all of this area is pretty much 100%. I say pretty much, it's not exactly, but pretty much. So again, this is what we do. This is, again, the general approach. I want to make sure you understand this. So it's the raw data. So we have the raw data and we transform it to the Z-score by this transformation. And the formula was, so we take the raw data, we minus the mean divided by that standard deviation, and we get our Z-score. From the Z-score, we can use the chart and we can get that probability. Also from the Z-score, we can go back and get that raw data by simply we multiply the left and right hand side of Z times our standard deviation, and then we can add that mean and we can get our X value. And from the probability, you should be able to see that if you read what's inside that chart, you're going to be able to get that Z-score by using that table and that chart. So just think of this picture of where you are at, which situation you're at, if you have probability or Z-score or raw data, and what is the question trying to ask you? Do we want to go in which direction, essentially? Do we want to go in? So find the probability that X is less than 25 if we have this particular mean and standard deviation. So we have our raw, so we can take our Z-score. Z is going to be X minus mu divided by our sigma, and we can calculate it as negative 1.69. So we know how to calculate our Z-score. Our mean, again, is 27.2. We can put that in, and we can draw a bell curve. So this is, of course, our raw data, our X values. Now, our Z-score, we've calculated it. We know our mean is going to be, again, it's going to be 0. And our raw data here was 25, and this translated into a negative 1.69. But it asks for the probability. So this is what it's, so the probability that, of course, X is less than 25, and I'm just writing it another way, is the probability of X minus that mean divided by a standard deviation was the same as 25 minus our mean. It's 27.2 divided by our standard deviation 1.3, which is equal to our probability of our Z as being less than or equal to this number 1.69. And then we can look this up on the table, negative 1.69. So negative 1.69 is right here. So negative 1.6, and then next digit is a 9. So you read it down. So the probability is 0.045. Which is right here, 0.0455. Is that probability all in here? Which translates to 4.55%. What about this one? Find the probability of X being less than 32. So we can, of course, say X minus our mean, which is given in the question, and our standard deviation, and we calculate 0.74. So here is our 0. Here is our mean of 30.1. We calculate 0.74. And this translates into a mean of 32. So the probability of X being less than 32, we translate it from X to a Z score. And these values are now in Z. And we calculate 0.74. So 0.7, and then the 4 is here. So it's 0.7704 is the value. So 0.7704 is our value, and we get 77.04%. So this, for this data, this is the probability. So how are we going to address the situations that we are not looking for the area to the left? Suppose we're looking for the area to the right. So this is about the trick of symmetry. Suppose before X is like less than a value, what about if X is greater than some value? How do we do like this particular question? So previously we were looking at Z is less than 0.74. But what if we care about probability of Z being greater than 0.74? Well, so less than was this area here that we just calculated, which was 0.7704, but we want to know this area. So it's going to be 1 minus the red, and we get 0.2296. So just notice if it's greater than or less than. What about if the probability of Z being greater than 0.74 is also equal to the same due to symmetry, just so notice this, it's equal to the probability of Z being less than negative 0.74. So we just look negative 0.74. We look at these and it's 0.2296. And we get our answer, which is the same. But it's just like, because of Z being greater than 0.74. So you can either basically take the complement or you can do it by symmetry. So there's different ways of kind of like doing these questions. So what about the area between two values? Like this is less than or equal to this value. How would we do this question? Well, if we care about like this, let's say the probability between 0.8, negative 0.88 is less than Z is less than 1.03. We care about like this green area, right? But the table gives us everything to the left. That's what the table gives us. So we could take like this whole purple area and then we could subtract this red area and then we would get the green area essentially. So we could like look up these values in the table, 1.03, which is this whole purple area, and then subtract the whole red area, which is Z as being less than negative 0.8. So let's just, so 1.03, 1.03, I believe is this value, 0.8485. And the other value was negative, just remembering what the values are, negative 0.88. And we look that up in the value table, so 0.1894. So just make sure like you draw like a picture and you subtract the correct value, and then you get your probability, which is this green area. So how to use this left tail style normal distribution. So again, this is a bit of a summary. So for areas to the left of the specified Z value, we use the table entry directly. For areas to the right of the Z table, look up the table entry for Z and subtract the area from 1. Another way, of course, to find the same areas to use this idea of symmetry of a normal curve and look up the table entry for negative Z. And for areas between two values like Z1 and Z2, essentially we subtract the table area, let's say if Z2 is larger than Z1. So subtract the area for Z1 from the table of the area of Z2. So take the larger and subtract the smaller from it. So this here, not sure why this cut out. So this probability, let me just kind of try to fix it. So find the area between Z is equal to 1 and Z is equal to 2.3. So we can make like this essentially like this transformation. So, so the larger area goes first, essentially. So that would be the probability of Z being less than 2.70. So that's that whole area. And you can see like that's the larger area because 2.70 is larger than 1. And then we subtract this red area, which is smaller than this number. And we can find like these values again in the. So 2.7 is right here. So that's 0.9967. And the other one is 1.00. So it's 0.8413. So you're able to like look those up in the table. And then again, it's just subtracting that taking the larger area and subtracting the smaller area gets that desired area that we're looking for. What about finding the area to the right? So finding like the probability of Z being greater than 0.94. Well, that would be like this particular area over here is what we're looking for. But the table only gives us the area to the left. So we're going to have to take 1, the whole area, which is 1, minus this area to the left. So we look up, so this is equal to 1 minus the probability of Z being less than 0.94. So please note like this example. So, and we can like look this up again on the table. So 0.94 is here, this column. So we have 0.8264. And we calculate our areas respectively. So this is students and everyone, people forget that it's to the right. So just notice if it's to the left, to the right, or to the center. What about like the area between like these two values? So we have the probability between negative 1.23 is less than Z is less than 1.23. Well, we take like that bigger area, which would be 1.23, and we subtract that smaller area of negative 1.23. And then we have to look these up in the table itself. So 1.23 would be here. So that's positive. And then we subtract the negative one here. Negative 1.2. I have to scroll up. That's here, I think. 0, 1, 2, 3. Here. Yeah. And we calculate our result. So again, it's just about drawing a little sketch, like noticing this is the larger area minus that smaller area. Find the area to the right of z equals negative 2.94. So this is a negative one. But notice the word right? So it's to the right. So it's all this area of z being greater than negative 0. Whoops, this should be a 2 here, or typo. So this would be negative 2.94. Let's just correct that. So that is the same as basically equal to 1, the whole area, minus the probability of z being less than negative 2.94. So that has been fixed. So the area of z being greater than negative 2.94 is just 1 minus the area of less than. So notice this. So we're using that rule of complements essentially, and we look up this area in the table of negative 2.94. So we can do that yourself. So you see negative 2.9 and then the 4 here. So we find that area 0.014. And we calculate our area respectively when we find that. So 1 minus 0.0016 is actually equal to 0.9984. And then we could put it in a percentage if we wish. This one, I won't ask you, this is a little bit difficult. You can try this if you wish yourself. So find the area outside of z equals to negative 0.94 and z equals to 2.67. So outside of those areas, and you can draw these with a diagram and try them. There's also practice questions that are coming up that I'm going to give you guys. So find the area to the basically between the mean and z equals negative 2.28. And you start with a diagram. So what is the mean? So the mean again is when z is equal to 0, because remember this is our z. So it's just understanding what is the mean? Well, that just means when z is equal to 0. But that's all it means, right? So here's where z is equal to 0. And between that and negative 2.28. So we take this whole area, but we know this whole area because of symmetry, this side, so let's color code it. So this side is 0.5, and also this side is 0.5. So we can take basically 0.5 minus this little area over here, the red area, because it's left side, and then we can find that area. So negative 2.28 is here. So you subtract 0.5 minus 0.0113 and we get our area. So that this green shaded area is between basically negative 2.28 and our mean. So it's just about being careful. What is the question exactly asking you to do? So I kind of like this question because I love ducks. So they're one of my favorite animals. So a population of ducks quacked on average, let's say, little typos here, of 25 times per minute with a standard deviation of 5. So we have the mean, so it's because it says average of, so that means basically mean, remember, it means average, which means mu is equal to 25 per minute with a standard deviation of 5. So we know that our standard deviation is equal to 5. A mallard duck, let's call him Donald, quacked 22 times, 22 times. So that's X is equal to 22. What proportion of ducks quacked more often than Donald? So you can say a let statement like let X be the number of quacks per minute. And we want to know what proportion, what is the question? So what is the proportion of ducks, so proportion, that quacked more often than Donald? So Donald quacked 22 times, more often, so greater than 22 is what we're looking for, because proportion is like, what is the percentage or how many quacked more? And so once we first understand the question, then we can kind of do it. So first, the idea is to extract that information. Oh, we could have just left it an average too. Whatever. So we start here where, well, we can start wherever. We could say Z is equal to X minus our mean divided by our standard deviation. So 22 minus 25 divided by 5 is negative 0.60. We know our mean here is 25, so that's where we first draw this, and our Z is here. And we can label, we can go from 0, 1, 2, 3, negative 1, negative 2, negative 3. Our standard deviation is 5, so 25 plus 5 is 30, 30 plus 5 is 35, 40, then we can go 20, 15, 10. So we can label our x's first. And then the proportion of ducks quacking more than Donald, the duck, is, well, X is greater than 22, but this is greater than. So we have to stop here. The table only gives us less than, right? Now we can convert this into a z-score. So this is going to be Z is greater than negative 0.60. Okay, but again, this is greater than on this side. We want, so we want this side, right? But the table gives us this value over here. So we can take the whole area, which is 1 minus that right area. So 1 minus the probability that Z is less than negative 0.60. Now we go to the table. So negative 0.6 is right here. So 0.2743. And we take that whole area, 1 minus that probability of that red area of 0.2743, and we calculate that green area that we're looking for, that probability. So let's say Mary received a score at the 85th percentile in her math class. What z-score is associated with the 85th percentile? So 85th percent is this area. Now we're going backwards. So this is a little bit different. So we have 85th percentile, but we don't know what the z-score is. So we want to know the probability that the Z is less than this number that we're trying to find, and it's equal to 0.85, which is that probability. So we can essentially look this up on the table. Oh, sorry, I forgot to say. So these numbers here are negative, and they go from very small numbers, like almost 0 to 0.5. Here, the positive Z values go from 0.5 to almost like 1. So we're looking in the table for 0.85. And it can be like a look. So look for the number that's closest to 0.85. Okay, I think I found it here. So 0.8504. We don't want to choose this number because this is further away from the number of, and this is very far from 0.852 because the difference, you look at the difference from the value that you're looking for, like let's say 0.85, and you look at, like if it's exactly the difference, you might average the two, like you might add 1.0, whatever that number is, plus and 5, like so the Z could be like 4 digits. But in this particular case, if one number leans towards 0.85, this one would be it. So our Z here is going to be 1.04. Sorry. Oh, so sorry. Thank you. So if Mary's average was 68 and the standard deviation was 3, we're looking for her actual math grade, the raw data. So the raw data is going to be X is equal to Z times that standard deviation plus the mean. So from reading that table, we got 1.04. Remember that is the values in the probability. So we found so we have 0.85. We found that Z score, which was 1.04. And we calculate, so we found that Z score. And then from the Z score, we can plug this in here and to find the raw data. And we get 71.12. Again, just to recap it, we have this probability. The probability, we look it up in the table. We find the Z score. From the Z score, we can use that to calculate the raw data by plugging the Z times the standard deviation plus the mean, and we get that raw data. So let's say Bob, we have a Bob, and scored 44% percentile. I like the name Bob, actually, on a standardized aptitude test with a population mean of 100 and a standard deviation of 7. So we have this mean of 100 and a standard deviation of 7. And what score did Bob get on the aptitude test? So what is this? And we know the score was 44 percentile, 44th percentile. So that translates into 0.44 is basically our probability. So the probability that Z is less than a particular number, because these will be less than, everyone was less than this number. So what is the number that Bob scored in order for to be 44th percentile? Well, we know that the mean here is at 0. This is where Z is. And this is the percentile that we have. So we have to look this number up in the table. So it looks like 0.4404 is closest to this. This one would be further away. This one would be further away. You look at the difference again. So this translates into a Z score of negative 0.1 and then 5. So that's this value here. So negative 0.15. So the probability here looks like it's Z is equal to negative 0.15. So that is our Z. Now, so our X is equal to Z times that standard deviation of 7 plus 100. So we get our what score, because he's looking for the score. So the score is actually the X, the raw data is what the question is asking for. So, and then we can find that using this method. So we went from basically the probability to the Z score to our X, our raw data. So it's just keeping track of like what we're kind of doing, our steps here. Now, given the standardized aptitude test that Bob completed had a mean of 100 and a standard deviation of 7, what percentage of test takers received scores between 95 and 108? So we want that probability of being between 95 is less than X is less than 108. So we're going to, in this particular case, we want to compute two Z scores because we want to transform 95 to, so 95 minus 100 divided by 7 is negative 0.71. And we then transform X into Z, and we transform 108 into our Z score. So 108 minus 100 divided by 7 is 1.14. So we get like these values. We can of course draw this like the raw data here between 108 and 95, and we know the middle here is 100. So, and we can draw our axis, and we know 0 is here, but and we found our Z scores is between 1.14, so very close to 1. Subtract this this red area, our other Z score is negative 0.71, which is above the 1. And then we of course, we look these up on the table, like we've been doing. So the first one is 1.14, which is here, I believe. So that one's that area, 0.8729. Subtract, what is it? Negative 0.71, negative 0.71 is this one. And we get our actual value here. So that's that whole purple area. Subtract that whole red area is the green area. And the green is the area between like those values. So therefore, 63.4% of test takers scored between 95 and 108. And we can, of course, do more questions here. So if the population mean is 10, and the standard deviation is 2, what is the percentile rank for a score of 6 or 11? So if we know that the mean here is, let's write it, 10, and the standard deviation is 2, what about a percentile score? So this is a little different. So we have the probability of X being less than 6. So we can translate this into a Z score. So X gets transformed to Z. 6 being transformed, so 6 minus 10 divided by our standard deviation 2 is negative 2. So this gets transformed. We can look this up in the table, negative 2 up. And I'll let you check like these numbers, which is 0.0228 and multiply it by 100. The probability that X is less than 11. So we can like look this up into it. The table, again, we transform 11 minus 10 divided by 2 is 0.5. So 0.5, looking these up in the table. So let's look them up. So negative 2 looked up in the table is right there. and 0.5 is right here. And we got our values. So what percentage of scores would be higher than 6 and 11? So for it to be higher, just the keywords of like basically understanding if it's the inequality is less than or greater than. So if it's greater than, this would be again transformed into the z-score, be 1 minus the probability of z being less than -2. We just calculated this from part A, which is 0.0228, and this would be higher. This would be the other side. And you could see if you added this and this together, you would be equal to 1. The probability of x being greater than 11, same idea, transform it into a z-score. We just found our z from part A, 0.5. So this would be 1 minus probability of z being less than 0.5. We found this probability again from part A. And if you calculate, add these probabilities, this one and this one together, you would get 100%. So we're going to talk about the z-score even more now in this section. So this is a bit of a summary. So the area to the left, so here is our 0, to the left is our z-score. Area to the right is equal to basically the whole area minus that area to the left. Or we can use this alternative approach if we wish. Let's say we want the area to the right. Well, is equal to the area to the left of the negative due to symmetry. And the area between two values is essentially equal to this larger area of Z2 minus like this little part over here. So you can kind of see these pictures. So another example, so like let X have a normal distribution with this particular mean of 10 and a standard deviation of 2. Find the probability that an X value selected at random from the distribution is between 11 and 10. So find that probability of 11 is less than X is less than 14. So we can compute, again, we know that the mean here is 10. So 10 is in the center, has a standard deviation of 2. So we can add like 10, 12, 14, 16, 8, 6, 4. Our center here again is 0. So we write 0, 1, 2, 3, -1, 2, -2, -3. We can compute like these z-scores, one for 14, when our raw data is. So again, like this is our raw data. So this is 14 minus 10 divided by 2 is 2. And this is our other raw data, 11. So essentially we make like this transformation. We're finding like this probability between 11 and 14. So that is the probability when like these z-scores is between 0.5 and 2. So just notice again that transformation. And this is that purple area, the whole area minus this red area gives us the green area that we're looking for. So, and we can like look these up on the table. I believe we did something similar with these numbers of 0.5 and 2, and we get like these values. Let's just, oh, sorry. So 0.772 is here and 0.5 is right here. So when you subtract them, you get the values you wish. So the lifespan of, let's say, a rechargeable battery is the time before the battery must be replaced because it no longer holds a charge. One tablet computer model has a battery with a lifespan that is normally distributed with a mean of 23 years and a standard deviation of 0.4. What is the probability that the battery will have to be replaced during the guaranteed period of 2 years? So 2 years. Oops, that was a mistake. So we have our mean, we have our standard deviation, we have a raw value. So let X represent the battery life. The statement that the battery needs to be replaced during the 2-year guarantee period means that the life span is less than 2 years. So X is less than or equal to 2. Convert the statement to a statement about the Z-score. So it's just going to be X minus our mu divided by our sigma, and we calculate it and get 0.75. So draw the normal curve for the situation and indicate the area corresponding to the probability that Z is less than negative 0.75. So again, this is our mean. We draw it. We draw our standard deviations, 0.75. And we can draw this. Our Z-score, again, this is 0, 1, -1, -2, -3. This corresponds to our negative 0.75. And this value here was, what was it? It's like 2, right? So like they correspond, and you can draw that situation. So find the probability that Z is less than or equal to negative 0.75 using that Z-score table. So you go negative 0.75, you look up in the column down here, and you go 0.2266. And you find your value. So what is the probability that X is less than or equal to 2? So less than and equal, or if one little point doesn't matter. So if it's less than, or if it's like exactly like this, it's the same number. A point does not matter when it's continuous. When it is discrete, it does matter. When it's continuous, a point does not matter, if you notice this little detail. So Z being less than or equal to negative 0.75 is equal to the same probability. They're the same, right? So we understand this. Inverse normal distribution. So sometimes we need to find Z or X values that correspond to a given area under the normal curve. This situation arises when we want to specify a guarantee period such that a given percentage of the total products produced by a company lasts at least as long as the duration of the guarantee period. In such cases, we use the standard normal distribution table in reverse. And this is what we were just doing. This is when we look up an area and find the corresponding Z value. We are using this inverse normal probability distribution. So these are just more examples. Find that Z-score such that 24% of the area lie under that normal curve, and it lies to the left. So we know that if this is 24%, this is 0.24, and we're trying to find like this value, we look it up in the table. So so 0.24, it's about here. If you choose this one, this is further away because this would be 0.002 away from 0.24. If you choose this one, if you add 0.00 like 11, this one would be closer. So you say it's negative 0.71. So it's the same idea, like find the Z-score such that 87% of the area under the standard normal curve lies to the left of Z. So we have to find that value that is less than on the Z table of 0.87. So we look them up, we see this goes further and further and these numbers get larger. This one gets smaller. This is the one that's closest to 0.87. So this would be 1.13. And this is our final answer, 1.13. So find the Z-score such that 32% of the area lie under the normal curve. lies to the right. So 32% is to the right. So just notice the keywords first. So this is the probability that Z is greater than question mark equals 0.32. Well, that's the same as the probability that Z is less than question mark 0.68. Because you would see if this is 32 and this is to the right, then the opposite would be 68 and to the left. So then we can just look up this into the table. So you would see here that it would be 0.47, I would believe, is closest to that value. Yep, and that is our value. So it's constantly about like looking these up in the table. More and more examples. So Magic Video Games, let's say, sells an expensive video games package. Does any of the students like video games in this class? Because the package is so expensive, the company wants to advertise an impressive guarantee for the life expectancy of its computer control system. The guarantee policy will refund the full purchase price if the computer fails during the guarantee period. The research department has done tests that show that the mean life for the computer is 30 months with a standard deviation of 4 months. So the computer life is normally a distribution. How long can the guarantee period be managed? Does guarantee period B if management does not want to refund the purchase price of more than 7% of the Magic Video Games packages. And you can think of this as laptops too, right? Like if they are trying to decide like when should the guarantee period be? Should it be like 1 year, 3 months, 9 months, etc., like until like they refund your package or give you essentially a warranty with your computer package? Or I think of computers because it's a larger expense. And so like they do it like this analysis behind the scenes to like determine such a thing. So they don't want more than 7%. So we have our mean and our standard deviation and 7%. So we want the probability that Z is less than this 0.07. We know the probability. So we can compute like the Z score. Whoops. So we choose negative 1.4 and then 8, because this one's closer to the actual value of 0.7. So we got our Z value here. Now, the question, if we go back to it, how long can the guarantee period be? So we reread the question essentially to make sure that we're answering the question correctly. So how long can the guarantee be? So we found our Z score and we did some calculations, but we're not done yet. So we have to just go over the question again to make sure. So how long can the guarantee period be? So we want it in basically months here, not in the Z score, because it's asking you what is the period of time. So we can calculate this. So we got our Z score, we did all the math, but we didn't finish the question. So the Z times the standard deviation plus our mean, and that gives us our raw data of this particular value converted into the raw data. So now we have 24.04% or 04 months is our answer. What if we only wanted 2%? So back to the question. On the purchase price, that's with more than 7% being returned. Let's say we're in a company and we wanted only 2% to make returns. So this is the probability is less than or equal to 0.02. We can look that one up on the table. So 0.0202 is closest to 0.02. So this is our number. So our Z value is negative 2.05. So we get our value, and then we can convert it to a raw data. So if we only want 2%, then so when we convert this, it becomes 21.8 months. So if we only want 2% return, so you can extend that warranty or that guarantee period to 21.8 months instead of the 24.08 months. And then that way you kind of maybe save the company some money. So the last example has us find essentially, sorry, I can't see, us find a Z values corresponding to a given area to the left or right of this value. So, sorry, I can't see something because the screen. So the specified area is between negative Z and Z, and we can use this following trick. So if you have Z on this side, it's the same as like this value, like there's symmetry here. If you have this area here is equal to essentially this area here, you can use symmetry in between the areas as well. So the area between values, like let's say negative Z to Z, this is a little bit more tricky. You could do 1 minus the area divided by 2. And then calculate like the Z values. So if you had the whole thing, you could divide by 2. So let's see like this more tricky example a little bit for the center. So find the Z score such that 90% of the area under the standard normal curve lies between negative Z and Z. So we have negative Z to Z, and we're trying to find the Z. Okay. So we want this, this area in here is 90%. So if this is 90, we know that this is going to be, the whole thing is going to be 100. So this is, therefore, this is going to be 5, and this is going to be 5. And you can check, like 90 plus 5 plus 5 is 100. Okay. So we want to find the Z less than or equal to, well, this would be equivalent of finding just this particular Z here of less than, let's say, 0.05 of here. So we look that up in the table. So you can put the answer actually as -1. So which one is closer to 0.05? Is it this one or is it this one? Which one do we go with? Anyone? Yes, exactly. You could take the average of the two. So we could say it would be -1.645. So we can actually, yes, take that average of the two. So we can take the average of them. So I think it's -1.645, if I remember it correctly. -1 just double checking. So it would be -1.64. Yeah, you don't want. So somewhere in between these two values is what we would take. Suppose the time to complete a test is normally distributed with a particular mean of 40 minutes and standard deviation of 5. How many minutes can we expect all but about 3% of the test to be completed? So we know 40 is exactly in the middle, and we know the probability of all. So how many minutes can we expect all but about 3% to be completed? So that means 97% of people completed the test is on this side. So we want the probability 0.97. We want to find that value here. That's that score. So it's just about reading the question. So the closest value to 0.7 is, it's not this, it's further away. This one is very close. So it would be 1.88. So we get our value, and then we can convert it to our raw data, and you get 49.4. So 49.4 minutes all but 3% of the students have finished the test. So almost 50 minutes. So basically, a class is usually about an hour, subtract 10 minutes for the 10-minute break and things like that. So the majority of the students, 97% of the students, finish that test in usually the regular allocated 15 minutes, which kind of makes